Hello and welcome back to another A-level maths video, A2 this time, and last time we did moments, this time we're doing projectile motion. Now again, A2 mechanics is very tricky, unlike A2 stats. I think that's mainly an extension of AS stats, but A2 mechanics can get really tricky and projectiles is no different. So we're going to do some really fun stuff. We have 5 questions which are very, very different from each other, which I will explain as best as I can anyway, and hopefully by the end of it you kind of gain a lot more confidence in how to answer these questions, because the actual method is the same every single time. But before we get started, I would like to ask that if you haven't subscribed already, please consider doing it if these videos have ever been useful to you at all. It really does help me out. It takes 2 seconds and yeah, I'd really, really appreciate it. So, getting on with projectiles, enough begging for now. So, at the end of kind of AS mechanics, we started talking about forces in terms of 2 dimensions, right? So you'd have a force, let's say 10 newtons, and it acts at an angle of 30 degrees, and we could then break this up into horizontal and vertical components, right? So horizontally you're looking at 10 cos 30, and vertically we're talking about 10 sine 30, and then we could do a bunch of like resolving and some fancy magic in order to work out a bunch of different things. The reason why we could do that is because they are vectors. Now with projectiles, when we've done SUVAT before, we mentioned that everything in SUVAT, besides time, is actually a vector. So everything except time. This means that we could have S, U, V and A in 2 dimensions, in the same way that we can have forces in 2 dimensions. And the good news is, just like we could do back with forces, we can treat them as completely separately. So we can resolve this motion going horizontally and going vertically, and we can treat it as 2 completely separate things, which is really, really useful. And although this is called projectiles, it should be noted that almost all motion in real life is some form of projectile, because we're not just moving left to right or up and down, we're moving some combination of all of them. For example, if I throw a javelin, it follows an arc like this. In other words, it has a vertical component and it has a horizontal component. And the key skill from projectile motion, this entire chapter, is being able to separate them into 2 different pieces and treat them independently of each other. The good news is there are no new equations. We're going to just use the SUVAT equations that we've used for the past year. The only new thing is treating it horizontally and vertically as separate. So let's get into a question. Let's see if we can sink our teeth into this. So a darts player throws a dart at a dartboard which hangs vertically. The motion of a dart is modelled as that of a particle moving freely under gravity. The dart moves in a vertical plane which is perpendicular to the plane of the dartboard. That sounds very complicated. A dart is thrown horizontally with an initial velocity of 14 meters per second and hits the board at a point which is 9 centimeters below the level of when it was thrown. So let's draw this out. It's being thrown horizontally, so straight to the right, at 14 meters per second. And then the actual board is somewhere down here, and that's 9 centimeters lower. Well, that might seem a bit weird, right? Because if it's going straight to the right, how on earth does it hit something down here? Well, don't forget that we have acceleration due to gravity going downwards. So this motion is actually going like this, and then it would hit the board down there. So it would go like an arc. In fact, it would be a little more steep than this. So if I want to make it slightly better, I might want to draw something along these lines where it kind of goes like this, and then it sharply drops down, which looks a little bit better. So, okay, it says find the horizontal distance from the point where the dart is thrown to the dartboard. So here's what you do in every projectile motion question, every single one. We're going to first look at the up and down motion, okay? Then we're going to look at the left to right motion. Now which one, again, just like I did in SUVAT, which direction should we take as positive? Well, it makes sense to take to the right as positive because our object, our dart, is moving to the right, and then also down as positive because it's also going down. So if we look vertically, let's look at S, U, V and A. S, U, V, A and T. Cool. What is the displacement from its original starting position? Well, it goes down by 9 centimeters. Again, we don't really care about 9 centimeters, we care about meters, so that's going to be 0.09. What's the initial vertical velocity? I'm going to say we don't know yet. However, some of you may have already pointed out we do know it. Now, A is it's accelerating downwards at 9.8. And we don't know the time. Right? We don't know when it collides. In fact, actually, do we? No. Perfect. I panicked for a second. Now, this is the weird part. When we look at the initial velocity here, can we see that all of it is completely horizontal? Right? Vertically, there is no velocity. It starts off with 0 velocity vertically. However, if I zoom in to any point along here, we have velocity going this way and some velocity going down, because now it's starting to speed up going down. So it's almost like we've released this from rest. So shooting it this way, initially it's moving to the right at 14 meters per second and it's not moving down at all, which means the initial vertical velocity is 0. Now, of course, we can calculate some stuff now, but let's have a look at what suvat is horizontally. Well, S is what we're trying to work out, right? The horizontal distance from the point where the dart was thrown. So this horizontal distance. So I'm going to say it's S because we don't know it and we kind of want it. U is equal to 14. Now, V, A, and T are going to be kind of interesting. Oops. What would the acceleration be? Well, it says here that the motion of the dart is modelled as a particle moving freely under gravity. When it says freely under gravity, it means the only force acting on this is gravity. If there's no other force, and again, bear in mind, gravity only acts downwards, it doesn't act to left or right, that means there's no other forces acting on this going to the right or left. Which means the acceleration going right or left is 0, because there's no horizontal forces, which means there's no horizontal acceleration, which means the final velocity should also be 14 meters per second. It's still travelling to the right with the same velocity as it starts off with, because we're saying there's no air resistance, there's no other forces acting on it. Now, of course, this isn't too useful, right? How can we work out S with U, V, and A being like this? Well, in this case, the actual distance formula is just speed times time. So it's going to be 14 times t. Now, what's t? T is the amount of time it takes for it to hit this board. So we don't know it yet, which means we now have to use our vertical motion. Okay, how do we use the vertical motion? Well, here's the point. When it drops 9 centimeters, it hits the board, right? Because that's what it says. It says, where does it say it? The dart is thrown horizontally. It hits the board at a point 9 centimeters below the level. So, just to repeat, when it drops 9 centimeters, it hits the board. So when S equals 0.09, that's whatever that time is, that's when it hit. That is the amount of time it takes to hit the board. So we have S, U, A, and T. So the formula I'm going to use is S equals UT plus a half AT squared. Now UT is 0 because we have U is 0. So we have 0.09 equals a half times 9.8 T squared. So if I rearrange this, I'm going to times both sides by 2. So we have 0.18 equals 9.8 T squared, which means T is equal to the square root of 0.18 over 9.8. And of course this is plus or minus, but do I care about the negative version? No, because time cannot be negative because it's not a vector. So we have 0.18 over 9.8, and that gives me a value of 0.136 seconds. Now if you think about it, that is a very short time. Does it make sense? Well, if I'm throwing a dart, how quickly will it hit the board? Pretty quickly, right? Like you throw it and it's almost immediately at the board. So that means our displacement now is 14 times 0.136. So all I'm going to do is I'm going to do 14 times answer. Ooh, that was careful. Gives me, let's call it Does it say how many? Let's say 1.90 meters. So, and again, this does make sense. If any of you have played darts, or if you've thrown anything, 1.9 meters is quite a long distance, but it doesn't drop by that much if you throw it quickly, right? It's the same concept as when you like fire a gun, for example. The bullet travels very straight because it's moving very quickly. It's still dropping at the same rate. It's just that it travels a much further distance before it drops by any significant amount. And that's it. That would be 4 marks, which I think is pretty good to an extent. But you're going to notice in every question that I do, we're going to do vertical and horizontal. That's it. You repeat over and over and over again, and life will be good, I promise. The next style of question they can give you is a very classic vectors question. Now, I have to admit, the way this is taught is kind of bad. So back in my day, back in the olden days, we used to have to do a lot of work with vectors in terms of IJ notation in order to work out things like, well, the angle at which the object is moving and all of this fun stuff. They've kind of removed that, which I don't agree with mostly, because it doesn't really appear in the exam very often, but when it does, it's always the worst answered question. So let's have a look at this. It says find the angle of projection. So the velocity is, well, I mean, it's a line going up and to the right. Why is it up and to the right? Well, because I and j are both positive. So it's going up and to the right. And that would give us the 3ki plus 2kj. Now, angle of projection means this angle here. Now, we can break this up into horizontal and vertical components. And the really good news about IJ notation is the first number is literally just the horizontal part, and the second number is the vertical part. And now it's a simple matter of trigonometry. So we have opposite over adjacent, so we have tan. So tan theta equals 2k over 3k. So that means theta is just inverse tan of 2/3. I feel like I've done inverse tan 2/3 many times. I feel like it's going to be at 30 something degrees. But let's see. Inverse tan 2/3. Not bad. 33.7 degrees. Cool. And then, given that the initial speed is 3 root 13 meters per second, find the value of k. So this here is the magnitude of the vector. It's the opposite side. And to work out the magnitude, it's the hypotenuse side. To work that out, all you have to do is do good old-fashioned Pythagoras' theorem. So we're going to do 3k squared plus 2k squared equals 3 root 13 squared. I know what you're thinking already. Wait a minute, why didn't you square root stuff? Pythagoras' theorem doesn't actually say the square root of a squared plus b squared is c squared. It does say a squared plus b squared is c squared. So it's easier in this case to leave it as squareds because we already have this fun thing here. So that gives me 9k squared plus 4k squared equals, so square root 13 squared is 13. 13 times 9, I'm just going to use a calculator because my brain's not working, is 117. So that's 13k squared equals 117. Divide both sides by 13, we should get 9 because we just got that. And that means k is equal to plus or minus 3. Now, there is no way to tell if it's going up, down, left, right, or whatever. So we don't actually know if it's a positive or negative. That's the key thing here. I drew this going up and to the right, but it could have also been down and to the left for all I know. But that's how you do that. The next 2 questions are where things are going to get a lot more spicy. In fact, the next question is where we get some really fun projectile motion questions. Yeah, check this out. This is a fun one. A basketball player is standing on the floor 10 meters from a basket, from the basket even. Shows how much I know about basketball. The height of the basket is 3.05 meters and he shoots the ball from a height of 2 meters. So, cool. At an angle of 40 degrees above the horizontal. The basketball can be modelled as a particle moving in a vertical plane. Given that the ball passes through the basket, find the speed with which the basketball is thrown. So, you know, when you're playing basketball with your friends, you can always do these calculations to quickly check. No, I'm kidding. So, what do we have? We have a ball. It's being thrown an angle, which makes sense again. If any of you have played basketball or watched it, they don't throw it straight up or straight forward. They throw it at an angle, which means it's going to... In fact, I'll draw this out once. It's going to go on a curve like this until it gets into the basket. But I'm going to remove that for now. The reason is because they shoot it at an angle of 40 degrees above the horizontal. Cool. That height there is 2 meters. The basket is like up here somewhere, and it's at a height of 3.05 meters. And that's all the information they give us. Cool. So given that it passes through the basket, wonderful. Once again, we're going to resolve horizontally and vertically. So what should we take? I'm going to take to the right, and I'm going to do something controversial. I'm going to take upwards as positive. So let's do the horizontal one first. Actually, no. I'm going to keep it the same as I did last time. Let's do the vertical one. S, well, it depends on how we define it, so I'm going to leave it like that for now. Now, U is interesting because I'm only looking vertically. So if I resolve this vertically, that is the opposite side of this triangle. It's U sine 40. Because again, I'm only looking at that vertical component. V, again, it depends on how we want to define it, but we know for sure that A is negative 9.8, and I have no idea what the time is. If we do the same thing horizontally, and literally we're going to label it the same thing, we don't know how far... he's 10 meters from the basket, so I did actually miss something. That's good. So the ball travels 10 meters. U is, again, it's going to be U cos 40 because we're looking at the adjacent part of this triangle. V should also be U cos 40 because here it says it's modelled as a particle moving in a vertical plane. So essentially there is no horizontal, there's no air resistance, right? So we don't actually care about that. There's no acceleration. And again, the time we're not 100% sure on. So now we need to think, what do we actually care about? Now, in order for it to get into the basket, there's a few different conditions that can be true. The first thing is, what is the overall displacement? So if we look at it vertically, the ball's going to go up and it's going to come back down. Now, for it to hit the basket, it needs to go up and then down and land 3.05 meters above the ground. Now, here's the thing. Displacement is from the starting point. So it's going to go up and down. It's only going to go up and down by 1.05 meters because that's the difference in those two heights. Like that. Hopefully that is relatively okay. Now, what I'm trying to work out is the initial velocity, what U is, the speed with which the basketball is thrown. Now, if I have a look at this, I don't have enough information here, right? Because S, U, A, and T, well, we have S, U, and A. I have no idea what V is, and I don't know what T is. Now, if I have a look at the other equation, we have S and U. Well, what could we work out? Well, just like in the first question, when we have zero acceleration, we can't use most of the Suvat equations. Because most of the Suvat equations depend on acceleration. So ut plus half at squared just becomes ut, you know? So a lot of them go away. But the one that we can use is just S equals ut. So 10 equals u cos 40 times t. Because speed is always equal to distance times... distance is always equal to speed times time. By the way, if you're wondering where that actually comes from, it comes from this. But when we have zero acceleration, that's what happens. Okay, I could now rearrange this for t, right? Now I can sub that in for here. What could I use? I have S, U, A, and T. So I could use S equals ut plus half at squared. This is going to be a fun one. So we're going to have 1.05 equals ut, so I'm going to call that u sine 40 times t plus a half 9.8 minus 9.8, sorry, t squared. So in fact I'll leave it as just this for now. Interesting. So let's expand this and see if we can simplify it. Because u sine, I already know what I'm going to do. It's just going to look hideous, by the way. So half, in fact, let me just, again, let's get out a calculator. Don't be afraid. 0.5 times minus 9.8 times 10 squared. So I'm going to do all of that at once because I'm lazy. Negative 490. Wait, hang on a minute. I should have subbed that in for t as well. Whoops. Damn it. Alright. A small mistake. Actually, it's not really a mistake. It's fine. Squared. So we're going to sub that in for t now as well. So I should have done that at the beginning. That's my bad. So, in fact, that makes my life a little bit easier, actually. U sine 40 t over, let's say, times 10 over u cos 40. Why did I put the t there again? The reason why I say this makes my life easier is the u's cancel out. Minus 490 over u squared cos 40 squared. Sine over cos makes tan, so this is 1.05 equals 10 tan 40 minus 490 over u squared cos squared 40. Now to rearrange this, all you'd have to do is times everything through by u squared, bring it all to one side and factorize it and do all that fun stuff. So what I might do to make my life easier is I'm going to move this 10 tan 40 over to the other side first in preparation for this. This, by the way, this looks horrific, but I promise you we're actually on the right track. Minus 490. And now all I'm going to do is I'm going to times both sides by u squared. So I'm going to put u squared on the outside. 1.05 minus 10t tan 40. 10 tan 40. My brain's shutting down. Minus 490 over cos squared 40. Divide both sides and then square root. So we're going to have overall minus 490 over cos squared 40 divided by 1.05 minus 10 tan 40, big old square root. Now, if you're worried about this negative, bear in mind that 10 tan 40 is bigger than 1.05, so it should cancel out. So let's enter everything onto our calculator. Negative 490 over, how do I want to do this one though? I'm gonna put this in brackets just to make sure it works properly. Like that. And divided by 1.05 minus 10 tan 40 gives me 10.7 meters per second, which is indeed the correct answer. So, in terms of our actual strategy, if you notice, the first question we did and this question that we did is the same thing, right? We write out all of our suvat for both of these, and for horizontal, we worked out time, right? Or we used time in some way. And it's always going to be the S equals, in fact, that doesn't even look like a UT, you know that? That's kind of annoying. It's always going to be the S equals UT formula. Why? Because A is 0, which means a lot of the other formulas become useless. So V equals U plus AT, useless, right? Same with the V equals V, you know, all of those questions, equations. They become useless because U and V are the same and A is 0. So we're just using S as UT. So I'm going to give you my strategy for now, right? So I've shown you twice. Vertically, you're going to write out suvat. Horizontally, you're going to write s equals ut and just sub in the values you know. You're then going to use that to try and eliminate variables to get to your answer. That's the general premise. Resolve vertically, do the same thing horizontally, but just use s equals ut, smush it together. That is the strategy. Part B, state two factors that can be ignored by modelling the basketball as a particle. Number one is air resistance. Number two, it can even be things like the spin of the ball, which is important in basketball. The weight of the ball, path changes, anything like that. Basically, it has no size, so we can also ignore its dimensions. Things like that. And here we come on to the final situation, the final question, and you're going to see that I'm going to do the exact same thing again. However, there is one tiny little difference, which is suggesting a suitable model for the motion of the ball. Again, this is why reading the question is so important. You can just read the previous questions and you know it's going to be particle moving freely under gravity. Right? So it's the same one that is in almost all mechanics questions, even in year 12. Particle moving freely under gravity is perfectly fine because a golf ball is very small, so the effects of things like wind resistance, etc. are not super important. But here we're hitting a golf ball, 49 meters per second. It goes on an arc, of course it does, 30 degrees to the horizontal, and the actual hole is 170 meters from O. So let's just say it's like here, for example, and on the same level as O. Oh, sorry. Maybe I should just say hole instead. Like that. And find correct to three significant figures the distance beyond the hole which the ball hits the ground. So essentially, we do care about the distance beyond the hole, but what we're trying to look for is how far the ball travels from the initial starting position. So again, what we're going to do is we're going to look vertically, and we have S, U, T, A, sorry, V, A, T. Oh my goodness. I did that the wrong way around. V, A, and T. And once again, when we do the horizontal components, we're basically just looking at S equals V, T. Now, we want the horizontal distance that this ball travels. We have the velocity, it'll be 49 cos 30. 9 cos 30. But we need the time. We don't know the time yet. So that means we must be trying to find the time from this one over here. Once again, I'm going to take to the right as positive. I'm going to take upwards as positive. So the displacement vertically, well, if you think about it, it pings off and then it comes back down and hits the floor. And that's what it says here, right? The distance beyond the hole at which the ball hits the ground. So the overall displacement is going to be 0. The initial velocity is going to be opposite, so it's going to be 49 sine 30. 9 sine 30. Technically we know the final velocity, but I'm going to leave it blank, but you can actually work out what the final velocity is going to be. But I'm not going to bother with that one yet. And then minus 9.8. And we do not know the time, do we? No, we do not know the time. Actually, so 2 equals 0, yep. Yep, perfect. So yeah, we're going to try and work out the time, and then we can use that to work out the displacement afterwards. So once again, we're using S equals ut, that's a half AT squared. So we have 0 equals 49 sine 30 t minus 4.9 t. So if I factorize this quickly, we obviously have two things here. I could factorize more out, but I'm just going to leave it as t equals 0. 49 sine 30 minus 4.9. So our first value for t is t equals 0, which makes sense because it starts off 0 meters from the ground. And the other value would be, that should be a t squared. There we are. The other value would be, well, if I write it out fully, we're looking for this equals 0. So that means it's 49 sine 30 over 4.9 is equal to t. So then my horizontal displacement is just going to be 49 cos 30 multiplied by 49 sine 30 over 4.9. And that should give us our horizontal displacement. Don't forget, that's not us finished yet, but it is close. Times fraction 49 sine 30. God, I can't read. Reading's hard. Over 4.9 gives me a total displacement of 212 meters. But remember, we want the distance beyond the hole. So the hole is 170 meters. We land at 212. So distance beyond hole is just equal to 212 minus, was it 170? 170. Which is 42 meters further than the hole. So he missed, lol. Okay. Then part C is an interesting one. Part C is a very interesting one. The magnitude and direction of the velocity of the ball when it is directly above the hole. So, when it's directly above the hole, that means the horizontal displacement is going to be equal to 170 meters. So we need to work that out quickly. So if we use S equals VT, we want the horizontal displacement to be 170 equals 49 cos 30 times t. So rearranging this, we get 170 over 49 cos 30, which gives me a time of something. Should we take a guess? 3.9? Why not, right? Not bad. 4 seconds. And we want the magnitude and direction of the velocity. So what we're going to do now is we're going to work out the horizontal velocity and the vertical velocity after the fact. So that's what we're going to do now. So it makes sense that the horizontal velocity stays the same because remember there is no horizontal acceleration, so still 49 cos 30. But the vertical velocity is going to be quite interesting. We're still going to use all of this suvat, except we can ignore. So S I shouldn't need to worry about. U I am going to care about. I'm going to call it 49 sine 30. V is what we're trying to work out. A is minus 9.8, and the time is 4 seconds. So we're just going to use V equals U plus AT in order to work out the vertical component. So this is the horizontal component of my velocity. We want the vertical component of it now. So here we have 49 sine 30 plus negative 9.8 times 4. It's going to be a very ugly number, I've got a feeling, which is fine by me. 49 sine 30 plus 9.8 times 4 minus 14.7. Now, does that make sense? Well, why is it negative? The reason why it's negative is because at that point, the ball is dropping downwards and going to the right. So this part is negative because we took upwards as positive, but now the ball's going down, okay? Which is why it's negative, which makes sense, right? If the hole's here, the ball should be dropping down at this point, unless he's overshot it by a massive amount. So that's completely fine. So now how are we going to do the magnitude and direction of the velocity of the ball? So we have something going to the right. In fact, let's work out 49 cos 30 quickly. It's probably not going to be a nice number, but that's just the way it is. I'm going to call it 42.4. So we're going 42.4 to the right, 14.7 downwards. 42.4. And we want the magnitude, so the overall speed, and the angle, which is just simple trigonometry and Pythagoras. So if we say the speed, that's just going to be 42.4 squared, so square root, answer squared plus 14.7 squared, 44.9, cool, meters per second. And then the angle is going to be inverse tan 14.7 over 42.4. Again, scoot the old calculator over. I can't even read my writing. 42.4. I thought it was 47.4 for a second. 19.1 degrees. So in other words, it's moving at a speed of 44.9 meters per second, 19.1 degrees below the horizontal. Which again, makes sense, right? Because it's coming back down to the ground. And that brings us to the end of projectiles. The way I've structured this video is I've done some very, very hard questions, to put it simply, because I think that as A-level students, going through the absolute basics isn't really too bad. It's when you get to the hard questions. So these are all from kind of like gold tier papers, Solomon papers, things like that. But if you want more videos on projectile motion questions, then do let me know. This is meant as kind of like a good overview. You have been exposed to all of the skills that you need in order to do any projectile motion question. But if you'd like some more, then please do let me know in the comments. I'm more than happy to make them. I really like mechanics, so I'm not going to argue with making even more videos on this. But hopefully you found that useful, and if you did, please consider please consider subscribing, which will really help me out. But other than that, I'll see you in the next one.